Hi, I'm Kevin Swiger with VPG Micro Measurements, and I'm here today in Bangalore, India with Vijay Kumar of Dynatech. Dynatech is our servicing agent in India, and today what we'd like to do is show you the correct procedures for doing the surface preparation and bonding of a micro measurement strain gauge. And I've been with micro measurements for 24 years, and Vijay has been doing this for even longer than I have, so we want to show you the correct way to do it. There's some good information out here on YouTube. There's also some misinformation, so we want to show you the correct recommended manufacturer's steps here. So the first thing Vijay will do in the installation, we want to show you the gauge that we're going to be using. This is Micro Measurements CEA series strain gauge. It is 13 self-temperature comp. We're going to be bonding this gauge to a sample of aluminum here. And the pattern is a 125 UW, very, very common strain gauge pattern. Gauge length is 1/8 of an inch, and the resistance is 120 ohms. So we'll get back to the strain gauge in a minute. We'll start right into the surface preparation procedures. And the first thing Vijay is going to do is to degrease the beam. Very important step. There's a lot of situations where a beam may have had a machining operation done to it. Machining oils can be left on the surface. Even just handling your finger oils that could be on the beam from it being handled, or any kind of part that you're putting a strain gauge on, you really need to do a degreasing operation. To do this, he's going to use the Micro Measurements product CSM3. This is a very powerful degreaser, and it's applied by spraying it into a gauze pad. If you spray it on the beam, it's going to evaporate very quick and it won't be as effective. If you spray it into the gauze pad, it's going to stay liquid for a longer time and allow you to work with it. So you can see Vijay is degreasing the entire beam, not just the location where the strain gauge is going to be bonded, because we don't want the possibility of dragging contaminants back into the gauge location. And you can see by the look on the gauze pad there that he's showing, we actually did remove some material. This is a very important step. The next step that Vijay is going to do is to do a dry abrasive. Now, to do this, he's going to use a wet or dry silicon carbide paper. The grit is 320. This is about the right grit on aluminum to give you the correct surface finish. To start with, this is going to be an operation that's going to smooth the surface. This is an extruded part here, so there could be some bumps on the surface. We just want to remove those. As he's preparing the surface, he's preparing an area that's actually larger than he needs. We start large and get progressively smaller, so we don't drag contaminants into the gauge location later. And we don't want to over abrade it. We're going to do 3 abrasive steps, and the next step is going to be a wet abrasive using Micro Measurements Imprep Conditioner A. And to do this step, Vijay is going to use the 400 grit wet or dry silicon carbide paper. The Imprep Conditioner A is a mildly acidic solution, highly pure, so it's a one-way container, so it's not going to contaminate or become contaminated. And this has the effect of removing oxidation from the surface. It can also emulsify some organic materials that could remain on the surface after degreasing. Now, the 400 grit abrasive is going to give us the correct surface finish that's recommended for aluminum. And we're creating some peaks and valleys, increasing the surface area so that the gauge adhesive has plenty of area to make contact with. The next step is going to be a drying step. We want to remove the material that we've sanded there and the conditioner A. Now, there's a specific technique here that Vijay's going to illustrate. You don't want to wipe back and forth. You want to wipe in one direction. So he's going to put the gauze pad down on one end and wipe through the gauge installation area all the way off the end. Then he's going to flip it to a clean side and start at that same location and wipe the other direction. If you dry or wipe back and forth, you're just going to drag contaminants back into the area that you've done a precision clean work on, and it's not going to be as effective. Now, to align the strain gauge later, we'd like to have a reference mark. Usually there's a specific location that you want to accurately position your strain gauge. On aluminum materials, we can produce this mark by doing a burnish using a pencil lead. Now, you don't want to scratch the surface. You don't want to modify the surface or create a stress concentration. This would go against what you're trying to measure with the strain gauge. So we want to be able to produce a mark on the surface that's visible but does not modify the surface, and that's the definition of a burnish. The pencil will actually flatten some of the peaks that we created through the sanding process without changing the thickness of the aluminum beam. So he's going to go back and forth a few times there, produce a pencil mark on the surface. You know, it depends on the material that you're bonding the gauge to, but VJ, what would you recommend for steel if you were working on a harder material such as steel?
Well, if it's a hard material which cannot be marked with a pencil, then we can use a ballpoint pen.
Excellent.
Which has a nice round ball in the front. That will not create a scribed mark, but it will burnish the surface and create the same effect, so that the mark is very visible under proper light conditions, and
right,
allows us to align the strain gauge properly on the beam.
Excellent advice. Now that BJ has produced the pencil mark, we're going to clean the lead off of there, and you can see the mark very clearly with the lead, and here in a second we'll illustrate the burnish that's left behind. He's going to use that MPrep conditioner A again, and first scrub in the direction that he marked, and then scrub along the direction of the grooves that he sanded to make sure that we clean deep into the sanded surface.
We also make sure that the liquid doesn't dry on the surface.
Exactly, very good point. Yeah, everything, this is why we use the gauze pad to remove the liquids with the one direction drying step, because if you allow the material to evaporate on the surface, all these contaminants that we're taking time to clean out are going to get redeposited. It's going to condense right back onto the surface, and we'll be left with a surface that really hasn't gotten any more clean than when we started. So again, he's doing the wipe in one direction only on both ends. And can you show the burnish there for the camera? Does it show up in the light okay? So you can still see a mark on there. The pencil lead is entirely gone, but we can still see a burnish mark that will allow us to accurately position the strain gauge. You know, if you're doing this in a lab, you notice what BJ just did there. He's got a stack of paper that he's working on, and that allows him to remove the top sheet and have a clean sheet right beneath it. So it's keeps the work area clean. Okay, the next step after using the MPrep conditioner A, which is an acidic solution, we're going to use MPrep neutralizer 5A. Now, why are there two solutions? The first one is acidic. It removes oxidation, aids in cleaning the surface, emulsifying organics. The last step here is to give us a neutral pH. This is going to be bonded with an adhesive called M-Bond 200, which is a cyanoacrylate. And those particular adhesives are very sensitive to the acidity of the surface. So to ensure that we cure the adhesive correctly and establish the best possible strain gauge bond, we're going to use the MPrep MPrep neutralizer 5A to bring the surface pH back up to neutral. And VJ's doing this with a scrubbing step in the direction that he sanded.
We can see that the surface is now coming out really clean because there's hardly any dirt seen on the cotton tip.
Right. You know, it seems like a lot of effort that we're putting into all the steps involved to correctly clean the surface, but it's very important if you want your strain measurement to be as accurate as possible and you're taking the time to install an expensive sensor, it's worth the time to do a proper surface preparation to ensure that the measurement later is not questionable.
If the surface is really clean, then when we wipe it for the last time, we get a good squeaking sound.
Squeaky clean.
Squeaky clean, yes. That ensures that the surface is ready for taking a gauge.
Good. Okay, now that the surface preparation is complete, we're going to set the beam aside and we're going to work with the strain gauge and prepare and position that strain gauge sensor. Now you notice VJ has a piece of glass that he's going to use to lay the gauge out on. Nice thing about glass is it can be cleaned very precisely, and it's actually easy to see if there's anything on the surface that's going to cause problems with the gauge. Everything that we handle the gauge with, from our tools to the glass surface we lay it out with, we're going to do some cleaning on. In this case, he's going to use that neutralizer 5A and just wipe the glass clean. We're not precision cleaning the glass like we did the aluminum, but we do want to make sure that there's nothing on the surface that's going to cause problems with the strain gauge. Even dust, you know, if there's dust in the air, dust on the glass, that can later form a bump under the strain gauge and can make the installation questionable. So now we have a clean surface to lay the gauge on. Now VJ is going to hang on to this package. It has the engineering data on the label that we're going to need later to correctly scale our instrument, and if we're doing anything with involved temperature changes, we're going to need that thermal output coefficient to correct our data for temperature. So we need to hang on to this package. The engineering data that's on this package is specific to the strain gauges and lot that is in that package. So it's not related to all strain gauges of this type. It's related specifically to the gauges in this package. You know, when you lay the strain gauge out, it's important that you lay it out shiny side up. The VJ will illustrate that, but the surface of the strain gauge on the bonding side has been treated, and it has a dull matte surface finish. That's the side that's going to be down on the glass and later down on the aluminum surface. So we're going to lay this gauge out shiny side up. Now you'll notice the tools that VJ is using. This is a blunt tweezer, and he's handling the gauge by the backing only, being careful to keep those tweezers away from the foil.
Yes, also we try and take the gauge, pick the gauge up from the tab end rather than
Correct.
from the other end, so that if in case there is going to be any damage, it will be on the tab and not on the
For
sensitive
sure.
grid.
Yeah, you don't want to scratch the sensing grid on the strain gauge.
We need to pick this strain gauge and then transfer it to the cleaned beam, and for that we use an installation tape called the PCT2M, and this helps us to pick up the gauge from the glass plate and transfer it to the
VJ, sometimes customers have asked, and it comes up pretty frequently, they say, what is special about this tape?
Yes.
And you want to comment on that?
It's a special tape picked out from a large number of tapes available in the commercial market. It has the property of not leaving its mastic on the surface, so the surface doesn't get contaminated when we use this tape. And that's the main reason why we use this tape and not any other cello tape.
Right.
With an ordinary tape, it's possible to put the mastic on the surface, and then the gauge will stick on top of the mastic. It will not bond, and we have failure.
Right. It's the right balance of tack.
Yes.
It's going to be tacky enough to bond the gauge, but yet be easy to remove. Also, it's very well tested. We
Yes.
know that mastic, the adhesive that's on that tape, is compatible with all the micromeasurement strain gauge adhesives. It can also handle the cure temperature range of any of the elevated curing adhesives. So it's very well tested. It's that's what makes it special, really.
And the tape is also mechanically stable enough to make sure that the alignment remains correct.
You notice it in the video here that VJ is pulling off that first piece of tape and throwing it away. Now, the reason is the dispenser that's used here. That tape, the first couple of inches, is left exposed to the air. Now, if this has been sitting in a lab for a while, in a toolbox or somewhere, it's going to have some dust and dirt on the tape. So we pull that first 2 or 3 inches off and then just throw it away. So now he's going to pull a clean piece of tape off. Now, I'll tell you another thing that I found in helping customers learn to install gauges. When we lay this tape out, we don't want to stretch it. VJ mentioned that this tape is dimensionally stable. It's very easy to, with just a small amount of tension, to put a large strain in the tape, and then when you seal it down to the surface, you could lock that strain into the gauge and have an offset later. So if you tack the tape down, as VJ is going to illustrate here, on one end, and then with almost no tension on the tape, slide your finger across, seal it down to the glass surface over the strain gauge, you have done it so that you have not put any strain in the tape that would later be transferred to the gauge. This is a very common way that people who are installing strain gauges can get a large offset. They'll stretch the tape very tight, stick it to the strain gauge, and then lift it up later, and that tape relaxes and it takes the strain gauge with it. You get a very large compressive offset. So the way VJ did this here is the recommended way to do it, so that you'll have a strain gauge that is close to its resistance tolerance.
I've also folded the end of the tape so that I have a handle to pick this up later without having to struggle to lift the tape off from the glass if I hadn't done that.
Yes. Good. Okay, so now we're ready to transfer the gauge from the glass to our beam. Now, the strain gauge has alignment marks. These alignment marks mark the geometric center of the strain gauge sensing grid, not the whole strain gauge, but just the sensing grid of the strain gauge. So that's what we want to get centered on the alignment marks. If you can see it there, you can see the triangles on the side. That's what VJ is going to align with this burnished mark. Now notice in the video how VJ picks the tape up. He's going to lift it at a very shallow angle. We don't want to crease the strain gauge. And once he gets past the strain gauge, then we can pull the tape off without regard to the angle as much. But as he lifts that tape off on the strain gauge, it's done at a very shallow angle so as not to crease the strain gauge. Okay, now visually he's going to align the gauge with the burnished mark on the aluminum surface. And using a very similar technique without putting a lot of tension on the tape, once he gets it where he wants it, he's going to seal it down to the surface. And keep in mind that if you're not pleased with how the gauge aligned the first try, you can lift it off the surface and realign it. So this is not something that has to be done correctly, or you can't go back and fix it. It's very easy to pull the tape off and realign it if necessary. Okay, looks good.
I think now it's properly aligned.
Okay. Now that the strain gauge is held in position on the surface, VJ is now ready to apply adhesive, and we'll get the strain gauge bonded. So he's going to lift this gauge again at a shallow angle, and he's going to lift it just a little bit, just a few millimeters past the end of the tabs, or the end of the strain gauge, to allow room for the adhesive to flow.
About 5 or 6 millimeters
5 or 6.
past the edge
Okay.
of the tape.
Now, here's a little trick that is worth mentioning. You know, that tape's going to want to flip back, but you notice what VJ is doing here. Once he gets it past the gauge, he's pulling it back 180 degrees on itself, and then giving a little tug further, and it will lay flat. He's going to tuck that end underneath there too, so he can still pick it up, but the gauge is going to be held back out of the way while we apply the catalyst and the adhesive. Now, the material that we're using here is M-Bond 200 adhesive. This is sold as a kit that contains this bottle of catalyst and a bottle of the adhesive. And the purpose of the catalyst is to speed up the reaction, the chemical reaction, and allow the adhesive to cure a little bit faster. it requires very, very little catalyst. So he's going to wipe that brush off several times on the inside of that lid. And we just want enough catalyst to wet the surface. We don't want to have any liquid that stands on the surface. We recommend applying the catalyst to the back of the strain gauge. You apply it to one surface only, and our recommendation is to apply it to the back of the strain gauge. Now, this has got to dry. The actual material that is the catalyst that causes the faster chemical reaction is not the liquid. It's suspended in the liquid, but it's actually a solid material that as the liquid evaporates, it's left behind as a layer, a very, very thin layer on the strain gauge. So just keep in mind when you're using this catalyst, it's not something that gets mixed liquid to liquid with the adhesive. It's allowed to dry, so we usually give it at least 60 seconds to make sure that it's completely dried before we apply the adhesive. The adhesive that we're going to use here is Embond 200. This is a cyanoacrylate instant curing adhesive. Sometimes people generically refer to this family of adhesives as a super glue. VJ, why is this adhesive special? Can you tell us the difference between this and the crazy glue variety that you might get at the hardware store?
Well, this particular adhesive is one that has been tested for its ability to bond gauges to the required specifications. The other adhesives that are available in the market are not tested in this manner. This adhesive is required to stick a strain gauge to the surface in such a way that it becomes part of the surface. We need it to stick that strongly. The normal adhesives that are available in the market are only required to stick two pieces together, and there's no special requirement for that to be really very strong. So the chances are that if we get a commercial adhesive and try to bond a strain gauge, we will not get sufficient adhesion between the gauge and the component to really measure strain accurately.
It's such a critical component. This is the material that's going to transfer the strain, the surface deformations from that aluminum to the sensor that's going to make the precision measurement. So, you know, it's very much worth it to have a gauge adhesive that's tested, has specifications for strain measurement, and we can rely on that to transfer strain so that we can arrive at an accurate measurement later. So what VJ is going to do to apply this, it just takes a single drop of this adhesive, and in fairly fast sequence here, I'll describe what he's going to do before he does it here because it's going to happen pretty quick. You notice that he's got a gauze pad folded, and that's going to be used to swipe the tape down once he places the drop of adhesive on the beam right at the tape edge. So he's going to get all that in position, ready to go. And within a few seconds of putting this drop down, he's going to swipe the gauge down. It'll land exactly in the position it was because the tape is still attached to the surface. And then he'll immediately get thumb pressure on this installation. You want your thumb to cover the strain gauge. And we often joke about the rule of thumb, if you'll pardon the pun, that if you have half a white thumbnail, then you're putting enough pressure on it. So
Yes.
that's our rule of thumb.
And we need to keep this pressure on for about 1 minute.
Yes, sir. That's right.
So we can have a stopwatch or look at the dial on our wristwatch. Now, of course, the mobile phones have a timer in them.
That's right.
And that can be set to one minute.
Maybe our director can help us out there.
Yes. So start. And once the minute is over, then we can release the pressure on our thumb. It's important to remember that when we apply pressure with our thumb, we don't deform the component. So especially if we are doing this on a thin component, which can deform quite easily with thumb pressure, it's important that we have a solid backing.
Something to support it.
Support it.
Yeah,
like
point.
the glass plate that we have underneath. Otherwise, we will have a deformed component on which we bond the gauge, and when we release our thumb pressure, it will spring back and we'll have a large tension on the strain gauge.
Yeah, another way to produce an unwanted offset. So that's a good point. And to help you out here, I'm going to put the lid back on this adhesive. You know, it's worth noting in this video that any instant curing cyanoacrylate is going to be very sensitive to humidity. Humidity will cause the adhesive to go bad in a hurry. So if you're working with it, you want to make sure that it's capped and uncapped and stored that way. Another point I would make here, VJ, while we're waiting for the cure, because after the thumb pressure, we're going to wait another couple of minutes before we actually remove the tape. The thumb pressure initiated the cure, and we got enough cure there that it's going to have a thin layer under the strain gauge. We're going to wait another couple of minutes just to be sure that the polymerization is complete, and then we can remove the tape. While we're waiting there, I'll tell you something else that's worth mentioning about adhesives in general is once you open this bottle, you don't want to put it back in the refrigerator. Yeah, you know, before you open it, you can extend the shelf life. It benefits from being refrigerated. But once you pop the top on that bottle, you don't want to put it back in the refrigerator. The reason is because when you squeeze out a drop of the adhesive and release the bottle, it's going to suck some air back into it. Well, that air has humidity in it. And what will happen if you put it back in the refrigerator, that humidity will then condense out into liquid water, and that will degrade the adhesive very quickly. So in general, once you pop the top on them, keep it stored at laboratory conditions and don't put it back in the refrigerator. Okay, so it looks like VJ's ready to remove the tape here, and it's been at least a couple minutes there. So you notice that VJ is pulling this tape 180 degrees back on itself, so we're not producing any lifting forces on the strain gauge.
We don't pull in this way, we pull the tape back on itself.
Right. You know, the important bond criteria for any strain gauge is shear. You know, adhesives can be characterized in terms of their shear strength or their tensile strength. Now, it's possible that you can have a very good strain gauge bond without having a very good tensile strength on the strain gauge. The important bond is that shear, that shear motion that's going to transfer the surface strain to the strain gauge. That can be very, very strong while the tensile bond is weak. So remember that this is a mechanical bond. There's no chemical bonding between the gauge and the metal. So that's the reason that we roughen the surface. And we want to make sure that the shear bond is as strong as possible.
Right.
Okay. All right. So VJ, we've got the gauge installed successfully, and now I believe you're ready to begin preparing the wire. The first thing VJ is going to do is use this paper drafting tape. Now, this material, it's sold by Micro Measurements. It's actually, in the world, you know, it used to be really common material. Paper drafting tape. It looks like it's masking tape, but it's not. It was used to hold down paper on drafting boards back in the days when people actually used drafting boards. And the benefit of this type of tape is it's very low tack. It's made to be applied to paper and easily removed. So it works well for masking the strain gauge for soldering. VJ's going to cover the sensing grid of the strain gauge and leave just a small area, about a square, really, a square geometry of the solder tabs exposed for application of solder. Now, the particular gauge that we're using here has an overlay. It has a polyimide overlay that protects the grid. This is especially important to use this tape if you're working with a strain gauge such as an EA series that does not have an overlay. And we want to make sure that sensing grid is covered while we install the wires on the gauge. So VJ is going to take a few moments here now and prepare his wire. This cable that he's using, I believe, is a 26 gauge 3 conductor. He's going to do a 3-wire quarter bridge connection to this strain gauge. More information, if you need it, on that topic on the Wheatstone Bridge and exactly what a 3-wire quarter bridge is on the Micro Measurements website. So he's going to twist the conductors, and the first one he's going to twist here looks like it's the red one. It's going to be twisted by itself, twisted very tightly. And then he's removing the insulation after that. Now the black and white are going to be twisted together. These are the two wires that are going to be common. Okay, VJ's got the wires twisted. He's now ready to pre-tin the wires with solder. You know, we're going to pre-tin the wires with solder. Even though this wire is already tinned, we're going to saturate the strands with solder, so it's a little easier to apply it to the strain gauge later. The solder, you want to explain the solder that you're using?
Yes, it's a 361A-20R solder. It has the lowest melting point of solders that are used for strain gauge work, and it is a eutectic solder, so it creates a very fine solder joint without the possibility of a dry solder joint.
Goes from liquid to solid instantly at a very specific temperature.
Yes. So that's the reason we use this particular solder.
Plus it has a rosin core.
Yes, it has flux already inside, so that helps to make the solder joint better. Helps the solder to flow and allows the solder joint to form perfectly. So we are going to use this.
You're going to tin the tabs first?
We can tin the tabs first. So we put the tip of the solder in the middle of the square. Have a pool of fresh solder on the tip of the soldering pencil, and then press down with the pencil on the solder and on the strain gauge tab. Then lift the pencil and the solder off at the same time. Repeat this process on the other tab of the strain gauge. And if the tinning is not satisfactory, then the process can be repeated on the tabs until we are sure that the tinning has taken place.
Okay, nice. You notice that VJ pulled the solder and the soldering iron away at the same instant. I always explain it like this: the flux that's in the rosin core of this solder, it's going to produce surface tension on the solder, which is what gives you the nice shiny connections. But the thing about flux is that it burns away almost instantly once it's applied. So if you want to prevent the Hershey's Kiss appearance of the solder connections, you know, with a little sharp point on it, the trick to that is to pull the soldering pencil and the solder away at the same instant, just as VJ illustrated. That's what's going to give you that nice rounded connection. If you pull the solder away first and then keep tapping it with the soldering pencil without the flux present, the surface tension is going to reappear and it's going to drag the solder with it. So that's the trick. You know, another thing that I'll mention here while VJ is preparing the wire is the soldering that he's doing is at a very low temperature. You know, with strain gauge work, you have to use a low temperature. The melting point of this solder is about 361 degrees Fahrenheit, and the tip temperature of this soldering iron is only about, probably about 550, only about 200 degrees hotter than the melting point of the solder. If you have a high temperature, your solder will go very quick, but it's very easy to burn the tabs off the gauge too. And the way that you accomplish the soldering with low temperature is you have to use a flat type tip, a chisel tip, or screwdriver type tip. The idea is you want to hold the iron level and get the entire surface, flat surface of the tip, in contact with the entire flat surface of the area of the solder tab. This transfers heat simultaneously to the foil at all points and allows you to make a very quick solder connection. A very common mistake in strain gauge work is to use a sharp pointed tip. Now that's going to apply a point heat source to the foil, and that foil that makes the strain gauge is extremely thin. It has no thermal mass. Therefore, the heat does not radiate out from that point. So you end up with a hot spot that the solder flows on and a cold spot around it that the solder does not flow, and you spend excessive time trying to get the solder on the tab. So just as VJ illustrated here, use a flat tip. Make sure the flat surface covers the entire tab at one time to transfer heat everywhere, and the solder will work much better for you. Okay, what VJ did here was he has saturated his lead wire with solder. This way everything is ready to go. The tabs are 10, the wire is saturated. It's going to be easy to make the solder connection a little bit later. Next thing VJ will do is trim the excess length off of the stripped ends of the wire there. And he's going to trim this so it fits within the tinned area of the solder tabs on the strain gauge.
Also, before doing the soldering, I'm going to separate the two bundles with a small nick between the red and the rest, so that we have a small amount of flexibility here to be able to align these two on the solder tabs on the strain gauge.
Excellent.
Now we need to hold this in place, so I will use a piece of drafting tape to do this.
And you notice VJ is putting the edge of that tape very close to the end of the insulation. He's also going to produce a shallow bend in the wire. He's illustrating that there. We just want to make sure that when the wire is taped down, it's being forced downward towards the strain gauge. Otherwise, you know, the end of that wire could be pointing up in the air and make it very difficult to solder with the wire trying to spring up in the air as you're working with it. So doing this, just make sure it's forced down against the strain gauge solder tabs.
We also use a sharp tweezer to position the wire right on top of the tin parts on the solder tabs. And now
that everything's held in position, you're ready to work with, you don't have to have three hands now. You got everything taped firmly in position. It's ready to solder. You can use two hands to do the soldering now.
always have a small pool of solder on the tip, which helps the soldering process. And it's done.
And it's done. And folks, you'll notice that VJ did this without using any external flux. We just used the rosin core solder to achieve very good solder connections on the strain gauge, which is a good thing later. You know, flux is useful when you're actually soldering, but it becomes a contaminant that can cause problems with your strain measurement later if it's not thoroughly removed. And that's in fact our next step. VJ's going to use the Micromeasurements M-Line rosin solvent to remove any residual flux. This will also help soften up the paper drafting tape and allow it to come off without putting undue stress on the gauge installation. He's going to first saturate the tape and work the brush around the solder connections. We want to be sure that we remove all traces of that flux because, you know, one of the tests of an installed strain gauge, kind of a quality check to make sure everything is good, is we measure the insulation resistance of the installed gauge. Insulation resistance is the resistance from the lead wire system to the aluminum, the conductive. We want to see at least 10,000 mega ohms there. And the one thing that we've used that will prevent that from happening, aside from You know, if we didn't have a real good solder connection like we had here, if the solder was touching the aluminum, that's another problem. But the one material that will cause that insulation resistance to be low is the flux. It's electrically conductive, and in fact the insulation resistance check is a test to make sure that we've removed it all effectively. Flux, in addition to causing low insulation resistance, which can cause increased noise in your measurement later, but also for long-term installations, that flux is going to be corrosive to the thin metal of the strain gauge, especially if excitation voltage is applied continuously on the gauge. So we want to make sure we've removed every trace of that. So we're going to do this 3 times, what BJ is illustrating here. He's going to blot it dry. Again, you know, the same idea is that we don't want to let that liquid dry on the surface and recondense the flux, then we're just spreading it around. So we want to first put it in solution with the rosin solvent and then absorb it with the gauze sponge to make sure that we've removed it. And we're going to, this is so important, we're going to do it 3 times. Okay.
All right. Now we need to anchor this wire. If we shift this wire while handling, it can rip the strain gauge off the surface, because the movement of this will be transferred to the heavy soldered connections over here. We have a very delicate strain gauge and it can pull everything away from this. So to prevent that from happening, I'm going to anchor this wire to the surface, but before that I'm going to produce a
put a strain
relief loop
Yeah.
in the wire by holding the wire down on the surface at one point, pushing down with a round wooden piece and pressing down the wire on the other side, which produces this loop over here. And this strain relief loop ensures that there's enough flexibility for the wire to stretch in case the beam goes into severe bending without snapping the strain gauge off the surface.
Right, it just decouples the wire from the surface strain.
And now we can put a piece of tape over here.
Okay, so BJ, you're going to use a piece of aluminum foil tape. This is Micromeasurements FN
FE-2.
FN-2 aluminum foil tape. And this is a good way to anchor to a surface where you can't always wrap something around it. This is very aggressive tape and it's very strong.
And once this is done, then any movement of the wire on this side will not disturb the solder connection and the installation is now safe.
Okay, so now we're ready to apply a protective coating. The coating that we're going to use in this application is Micromeasurements M-Coat A. This is an air drying polyurethane coating. And this is mainly used for lab applications. You would probably not want to use this coating. You'd want to use a different coating if this were going to be an outdoor application or on a component that was subject to some sort of chemical exposure. We have coatings that work for that. So this is a brush-on coating. It's just brushed on in a thin layer, and it's a very good humidity barrier. It will seal things to the surface like that wire. You want to make sure it's around the wire, over the wire, and even under the wire at the loop. And once this dries, it really ruggedizes the installation. With that lead wire anchored and this coating in place, you've got a barrier against humidity damage to the adhesive, and something that's going to ruggedize it against being scraped off easily. So at this point we have a strain gauge, and once that coating dries for a short amount of time, we're ready to make a strain measurement.
That's right.
Excellent job. Thank you, BJ.
Thank you, Kevin.